I don't know how to choose things.
Okay, so let's start. So next speaker is Sarah Dean from Cornell, and she will be talking about learning and decision making under observer effects. So thank you, Sarah.
All right, great. You can hear me. I think I hear the microphone. Cool. Yeah. So yeah, thanks for inviting me to this workshop. I'm going to talk about something from a little bit of a different perspective in I guess maybe reliable machine learning in the sense of kind of learning theory, and decision making kind of and control theory. So let me not spoil it too much. Let me start with the maybe same motivation that many of us are thinking about here, in a very broad sense, which is, you know, AI, whatever that means, maybe to be more specific and not use kind of a marketing term. I think what concerns many of us are the existence of these large scale automated systems, which are enabled by machine learning. So whether these are kind of classical physical, cyber physical systems like robotics and automation, chemical plants, these sorts of things that are traditionally within the domain of kind of hard sciences and engineering, or kind of nowadays increasingly, like we've seen at many of the talks, kind of outside of this purely physical domain, thinking about things like news curation in social media, e-commerce, chatbots, and interpersonal communications are also now mediated by large-scale algorithmic systems, which have some kind of machine learning component, are able to learn and adapt from data. So these are the kinds of things I think about, and I think about them, I try to at least, under a somewhat kind of unified perspective, right? Where, you know, all of these different settings are some type of environment in which we as computer scientists are thinking about or designing or deploying some types of learning and decision-making algorithms. And so automated systems and machine learning, if we want to understand what's going to happen and make sure we're designing things responsibly, maybe we fall back on kind of the principles and pillars, which would be kind of control theory coming from the side of automation and decision-making, and learning theory, thinking about how we can guarantee that machine learning algorithms will work. So this is the intersection that my talk will be about today. Cool. So just to outline a little bit what I'll say specifically, I'm going to spend some time just kind of motivating the setting that I want to study, giving some background both on like myself, my own research path, I guess, on my way to this problem that I then want to focus on from these perspectives. I want to focus on learning dynamics, learning from data of a dynamical system with guarantees. And then I want to talk about optimal control for that system. And yeah, these two pieces are kind of work from the past year, very much ongoing, things that I'm excited about thinking on. So I'm happy to have questions and happy to tell you all about lots of open problems. Okay, but just maybe starting with background. I'm going to tell you first about linear quadratic control, a very simple optimal control problem that I spent a lot of my PhD working on. And then I'll also kind of tell you about preference dynamics, thinking about dynamics outside of the physical world and, I don't know, in our mental or human world. So let me start with the sample complexity of control. This is sort of the perspective that I'm taking in my work for this whole talk. This is work that I did a while ago, not quite a decade ago yet, but a while ago with my co-authors here, actually during my PhD, Horia, Nick, Ben, and Stephen. And we were kind of motivated by, in 2017, the excitement around reinforcement learning, right? If we can remember, I guess reinforcement learning is now exciting again for a different reason, which maybe we'll come back to a little bit. But at 2017, it was exciting because it had all this success in the game of AlphaGo, and was also being kind of widely touted as a solution to many robotics problems. And so the classic reinforcement learning setting was kind of these discrete problems inspired by games where, you know, safety is not really concerned, these are not really physically manifested in the world. But they were kind of applied to continuous systems interacting in the physical world, like cars and robots. And I think this is still happening today, but it was especially, there's a lot of special excitement around this in 2017. I think since then we've maybe learned more. And so what is sample complexity? It's a particular lens on this. It's saying how much data is necessary to control a system. right? In particular, we're saying if you give some error epsilon, that's like a performance specification, and some probability delta, that's like the risk tolerance of failure, how many samples do you need to observe in order to guarantee that the probability that your suboptimality is greater than epsilon? So your performance is degraded by no more than epsilon with probability less than delta, right? This is the kind of canonical sample complexity problem. And it maybe gives us a sense for like, how many hours of driving a car do you need before we can say something rigorous about them. In the end, actually, I think talking about safety in self-driving cars is much more complicated for reasons that we all know, but bear with me for this problem setting. Okay, so we sought to solve this problem in kind of a tractable setting, in some ways like the simplest setting you could think of, which is a control problem on linear dynamics. So this Markovian state evolves according to linear dynamics on the previous state and on the control input. Quadratic cost, so we care about minimizing a quadratic cost. We want states to be small and inputs to be small, something like regulation, stabilization, without too much energy. That's kind of what that means. And let's say some zero mean noise is disturbing the system. So this is like a classic problem. I'm not sure how many people here have any kind of control background, but this is something you would take in a class on, like, you would talk about in a class maybe on linear or optimal control for sure. And one of the reasons it's so famous is because it has such a simple kind of closed form solution that can be computed and defined in terms of the problem parameters A and B, the dynamics, Q and R, the cost. And it's a linear form. It says that you should choose inputs as a linear function of the state. And in this finite horizon problem, the linear coefficients kind of are defined recursively over time. We can also think about the infinite horizon version of the problem. Both are well posed. And so that was the problem that we worked on in 2017, and it kind of spurred a big line of research at the intersection of controls and machine learning and online learning, thinking about linear control problems. There's a couple generalizations and variations on this problem. One that's also kind of canonical from the control perspective is to add in partial observation. And that's relevant to my talk later today. So, in many real world systems, you don't actually observe the state. As much as this is kind of an assumption underpinning a lot of reinforcement learning work, it just isn't true in, I was going to say much of the physical world, but many other non-physical worlds as well. It's hard to observe the entire state. Luckily, classic control theory sort of has a template for how we could think about this. And that template is you kind of add in, again, we're sticking with this idea of linearity. So linear systems, we have a linear partial observation. So Y is now the observed signal that we can make decisions on the basis of. It depends on the state, and there is, again, some noise. And so it turns out this optimal control problem, despite this difference between having first observed the exact state of the system and now not observing the state of the system, the solution only changes a little bit. It changes as follows. Instead of having a policy, a controller that's linear in the state, I have to be linear in an estimated state, x hat, because I don't observe the state. But I just kind of replace x's with x hats, and I'm pretty much good to go. But of course, what is x hat again? X hat is just my best estimate, the expected value of the state, given everything I've observed. So given the inputs that I've chosen and given the outputs that I've observed. And so this optimal policy is unchanged. It's literally the same exact optimal policy I showed you in the fully observed case. It depends on the parameters of the problem. X hat now also depends on the parameters of the problem, and it depends on a couple more parameters. So it depends on this observation matrix, it depends on the noise characteristics, and it depends on the initial state distribution covariance. Okay, but in some sense, it's still a closed form. And furthermore, I'll say that in a second. What this fact that I can just replace x with x hat and move on with my life, I can apply the lessons that I learned in the state observed case now to the partially observed case, is called the separation principle. And this is something that holds in this symbol setting, does not hold elsewhere, which we'll discuss later, but it's still kind of a driving idea that powers a lot of classic control style approaches to problems. It says, I do whatever techniques I need to kind of estimate the state of the system. And then separately, I design a state feedback control policy. And I can kind of think of these as separate problems. And in fact, there's some people who kind of work on one side of that or the other side of that, not necessarily their intersection. And the last point I'll make here is that when the noise, the process noise and the measurement noise are Gaussian, then the estimated state isn't just some complicated expectation depending on these parameters. It's actually efficiently computed with a Kalman filter, which recursively updates the state. And a Kalman filter is linear in our observations and our inputs. So again, even the filtering step kind of remains linear as long as the noise is Gaussian. So we have kind of both this separation principle and this linearity. Okay, so that was like kind of a controls 101 background. Recalling our setting, we are curious what happens when you don't know the system ahead of time. You don't have like nice physical models of it. This might be something complicated. All you can do is observe inputs and outputs from the system. So specifically when these dynamics parameters are unknown. So we can no longer follow this procedure exactly because we don't know the parameters. Okay, so I'm kind of crudely summarizing, 5 years of work that have thought about this problem and thought about how to solve it in some kind of like statistically optimal way. But in this crude summary, I would describe the strategy as follows. First, just collect data from the system. Let's say N is the amount of data you collected. And then estimate the unknown parameters. So do some learning, do some statistics or whatever, some parameter estimation. And then just use the estimate as if it's true. Forget that you actually learned and just use that estimate if it's true to design some policy pi hat and then deploy that in the true system. So in particular, kind of caricaturing roughly what a lot of approaches do, while you collect data, you might input white noise. So choose some like random inputs that are kind of well spread. So their covariance is full rank. And how do we actually learn from observations? Basically just do some kind of least squares regression. The precise formulation is a little dependent and maybe it requires a little bit of thinking about the structure, but in the end of the day, it's a linear system. And so we can use like linear least squares regression to learn parameters. So the simplest possible exploration, maybe the simplest possible learning algorithm or continuous space learning algorithm, and then the simplest possible control, just apply the standard control. And informally, what happens in this setting is that the parameter error for this approach kind of scales like 1 over square root n, where n is the amount of data that you have, which is kind of the learning rate that we would expect. And the suboptimality of the policy kind of scales like the parameter error squared, in particular because we have a quadratic cost. So it's kind of natural to expect that if we're off by epsilon in the parameters, maybe we only pay epsilon squared in our suboptimality. And indeed, this is true with an asterisk, which means that overall we have this 1 over n rate on suboptimality. So if we want a small error, we need to collect many samples and the error decays at a rate of like 1 over n. Okay, that's kind of a caricature. I'm glossing over some stuff that is honestly interesting, but not for my purpose today. The conclusion is kind of actually this very naive exploration is essentially optimal. We don't actually need to think hard about the interface of learning and control. We don't need to worry about this inexactness. Like we can just do this kind of naive exploration. And in some sense, this is kind of the conclusion of this long line of work. So what did we learn? We learned that simple model-based approaches work. So model-based because here we actually estimate an unknown system and then use the estimates to design a policy, in contrast with the model-free reinforcement learning where we learn policies in a more black box manner. Naive exploration is also sufficient, or even actually in some cases, in particular in the partially observed cases, we might not even need any exploration. We might gather rich enough data already from the system without further intervention. So we don't really need to worry too much about exploration as much as like reinforcement learners will tell you that there's this whole trade-off, maybe not in this system. And then also when we design our policies, we don't actually have to account for this uncertainty. Just do machine learning and then use what you get, right? Kind of throw everything away. Now, there's some exceptions, and especially this is stuff that I've worked on. Like my early work in this problem was actually very much focused on robustness in the low data regime when your errors are not have not shrunk enough for all of these guarantees to kick in, or when you actually have some safety or actuation limits on requiring the state remains in some set or requiring that the inputs remain bounded. Then things are a little bit different, and accounting for uncertainty is more important. But if I kind of look at this, there's two things you could say, which is like, these are great takeaways and we should just apply them. Just let machine learners take over the world and not worry too much about it. But I tend to think maybe there's something missing from this simple problem setting, and that maybe we can learn more from something more challenging. So I would say this kind of linear problem, well, we learned a lot and it kind of spurred this kind of understanding at the intersection of optimization, machine learning, control. I don't think this problem captures all issues of interest. And I think continuing to focus on the linear setting, it's not clear what else there is to learn. So, okay, that motivates me to think about what new settings do we need. And I'm going to call this, that's what I decided to call it in my talk title. I'm kind of workshopping if this is a good name for it, is observer effects. So I was inspired by this talk I saw by Davide Scaramuza at L4DC, a conference on learning and control, about his work, which was published in Nature, on superhuman drone racing. So this is really cool. I think back when I started this line of work, it was kind of superhuman's performance in the game of Go. That was cool, but it honestly wasn't as exciting to me. I don't games are not that exciting to me. They're cool and I understand people like them, and I think the documentary does a really good job motivating the human element of it. But I thought this kind of stuff is much cooler. Not that I'm a very good drone racer myself, so I'm honestly just impressed by the human performance in some sense here. But we actually got superhuman performance, and yeah, it's just exciting. I think I have a little bit of time to just try to show. Let's see. No, I don't want the noise. Let me just show you what these drones look like. So this is a quarter of real-time speed, by the way. Normally robotics videos are sped up. This one is sped down, so you can kind of see it. But there's just kind of these crazy acrobatic movements where the goal here in drone racing, I guess I should explain, is to go through all of these gates in the right order. That kind of defines the task. And you can see these gates have markers on them for computer vision to make them easier to identify. But it doesn't actually mean they're easy from the onboard camera to identify. You can see here, right? You're moving very quickly, things are blurring. Depending how you're facing, that really depends where the camera can pick up an image. Okay, so I'm not gonna watch this whole video, although it is a cool one. But one thing that Davide emphasized in his talk was that actually classic optimal control methods did not work for this problem. They were much worse than the human racers. And I think the biggest thing, the emphasized reason for their failure is that they did not mix this perception and control ideas together. So in the video, I'm not sure if you saw this maneuver specifically, but here's an example where you have to go through this upper gate and then through this lower gate. And if you look, actually both the human and the reinforcement learning algorithm are doing the same thing, roughly, which is they are approaching this first gate. Before they go through it, they turn around and then they come this way. And why do they do that? Because on this side, they need to see where this gate is in order to go back through it. So you're kind of anticipating already the need to look in a certain direction purely because of perception, right? There's no kind of physical speed flying reason to turn around. It's only because there's some uncertainty in where you are and you need to see this gate to localize yourself.
Excuse me.
Yes.
Do they know they will have to go this way, or do they do that? Will the next gate maybe be somewhere further?
Yeah, so I think, okay, yeah, that's a good question. So
because then,
yeah, so for the superhuman performance, there is a set racetrack. And this racetrack is set also for the human racers. And they both the human racers and the reinforcement learning algorithms spend time practicing on that particular track. I think the human racers spend less time than the reinforcement learning algorithm needs data. So human drone racers have learned a lot of things that, this one little reinforcement learning algorithm, actually, I think did come with some simulation-based initialization, but yeah, still use this particular track. So yes, essentially, by the time you're here that you're going to have to do this maneuver. Yeah. Okay, so what's going on? I think a summary of this is kind of the observer effect, which I think is actually traditionally framed as sort of like the active observation is disturbing your system. I'm kind of generalizing a little bit to just say any kind of coupling between actuation and observation. And so the examples that I would think of are things, like electronic circuits and quantum wave collapse are these classic examples where you want to measure your system, but you just end up messing with it. In cases like human psychology, I guess kind of similar thing. You ask somebody a question, you want to know something about their underlying mental state, but the act of being asked and answering a question actually could change that. And then, cases like robotics where the disturbing the system is not so bad. We actually want to move the robot around, but in doing so, there's this kind of coupling between how we move and what we can see. Okay, so I think that's a widespread phenomenon that is interesting and maybe not captured in this LQR problem. So I'll spend just a little bit longer kind of motivating a particular type of observer effect based on some work I've done in recommendation systems, so personalized recommendation. I'm thinking kind of here of content recommendation. You could also maybe think of this as kind of interaction with a chatbot that's personalizing. I think roughly this holds where from the algorithm is recommending something to some environment, to something unknown. Actually, it's a person, but the algorithm doesn't really know anything about the person. But what the algorithm can observe is express preferences in the form of likes, watch time, clicks, that kind of thing. Classically, I guess if we wanted to take a algorithmic learning theory perspective on this, we would say, oh, this is an online decision problem where we need to simultaneously learn and make good decisions. And so multi-arm bandits is kind of our framework for that, where we end up modeling this person as having kind of unknown parameters theta that determine their preference. And in some way or another, we hope that in expectation, the observed signals are kind of equal to a linear function of those parameters and of some embedding maybe of the recommended content. So we have some inner product there. That's a classic problem. If I take my observer effect hat and look at this, the approach is to kind of ultimately identify these unknown parameters just well enough to make good recommendations. So this is kind of the explore exploit problem. We don't necessarily need to learn everything about somebody's preference. We just need to learn enough to pick from some finite library of content that we're making recommendations. But with the observer effect hat on, this may not be some static process, right? I don't think people are static. I don't think we have an unchanging preference parameter, rather maybe like a preference state. And if I call the preference state X, I can write this as an inner product between X and U with maybe some matrix to account for different dimensions. And that state will update based on the recommended content. So music you listen to might change what music you like. And so I don't have that much time. I'm going to go a little bit fast here. I just want to point out, I want to show you a model of preference dynamics that I've used in some work that is kind of taken as a given. So there's no learning here. This is just saying, what if the preference dynamics take this form, where we can kind of capture an idea of assimilation, where in a user's preference, X, right, is some vector. And when a recommendation is made that, let's say it's also living in the same latent space, U, the resulting preference will be some kind of combination of the two. Let's say it's some kind of some linear combination of the two. And then what does the system observe about this user? It observes how much the user liked that particular recommendation at this particular time, which is now this inner product. Okay, so there's a couple of different variations we can do. These types of opinion dynamics have been used to try to understand polarization from a mathematical perspective. I use them to think about personalized recommendation algorithms. And just to high level summarize, we kind of show that when you have this malleability in preference, you don't actually need to learn about somebody to make good recommendations for them. You can kind of get them interested in what you have to show instead. Instead of polarization being the concern, when you have personalized dynamics, It's more kind of like a collapse towards a couple different modes of available content rather than two poles, which kind of had been studied previously. We kind of show that randomizing can prevent some of these bad outcomes if you believe the model. And then I also did some work to show that you can use this to think about safety and harm. So even if harmful content is not recommended, your recommendations could shift somebody's preferences in the direction of harmful content, increasing the chance that they go and seek it themselves. And so if you take that modeling perspective, you can kind of score items differently for recommendation. So this work kind of takes these models for granted. And I think there's a lot of interesting stuff to say, but at the same time, I don't think this particular set of equations that I have here describes exactly how I think about music or how my music tastes change, but maybe they're a starting point. And so if we look at their form, we do have kind of linear, like a linear state update, and then we have a bilinear observation. So the observation depends on this product of input and output, right? This is not the linear case that I kind of introduced before. This is now kind of fundamentally has some interaction. Maybe the simplest interaction you could have, but it's some interaction. Okay, so that's kind of the model I want to think about when we talk about now learning dynamics and doing optimal control. Okay, any questions? I kind of like set the stage. So having set the stage, I can dive in and tell you about what we know so far. So let's say we want to learn dynamics in this kind of setting where we have bilinear observations. We don't know the dynamics, the state update, and we don't know the measurement function. So we don't know how Y is generated from the state. We observe a trajectory of inputs, which I'm going to say are p-dimensional, and outputs, which will just be one-dimensional for now. So yeah, our running example is, the inputs might be kind of attributes of playlists that are recommended to users. The outputs, like a personalized playlist on Spotify, for example, the outputs could be the listen time on that particular day, how much of the playlist did the user get through. And our goal is to actually identify this user from data. So understand the dynamics and understand the measurement model. And we're not going to solve this in general. I'm going to consider this linear bilinear setting where we say that the preference state updates linearly, just like I've looked at earlier in the linear quadratic control problem. And we have this partial observation, which is almost the kind of normal linear partial observation, except that we have this product with U. Okay. So how do we identify these unknown dynamics? I'll tell you about the algorithm. Yes.
A quick question. When you say identification, you mean like identify important feature of the user or literally identify the user?
So I'm using the control word. It's the statistics word is parameter estimation. So I'm looking to estimate these A, B, and C parameters. Sorry.
Okay, thank you.
Yeah, in control, estimation means state estimation. Identification means parameter estimation, right? It depends what you consider a parameter or not, I guess. But yeah, good question. Good. I'm happy to clarify that. So the identification algorithm, or the parameter estimation algorithm, is right. The input is some data. We're also going to have some parameter called history length, which will play an important role. And we may need to know the underlying state dimension depending on what kind of guarantee we want. So for now, let's just say that we know the underlying state dimension. Of course, something you'd want to relax. And our data looks as follows, right? We have inputs and outputs over time. So the first step is regression. And we're regressing for some parameters that I'm going to call G hat, which tell me the relationship between the output at time t, y, and both the input at time t, u, so like how did this user listen to this particular playlist, but also kind of the linear sum of these past inputs as well. So I'm not just looking at today's playlist, but actually the L previous playlists. So I'm capturing some notion of history that depends on L. And then that gives me some parameters G hat. The second step of the algorithm is to decompose from G hat the matrices A hat, B hat, and C hat and get the state space realization. This is where I need to know N. this uses a classic algorithm called Ho-Kalman. I'm not actually going to focus on it today. I don't have enough time. And it's kind of exactly as it's used in the linear case, which is why I won't focus on it. So we'll just focus on this first part of learning this history input-output map jhat. Because our goal, like our version of reliability or trustworthiness, is to have guarantees on our errors of estimation, like how incorrect could I be? And so let me introduce a little bit of notation to state that. So we have our jhat from our algorithm. I'm going to claim without proof for now that this is a biased estimate of the Markov parameters of the system, a version of the Markov parameters. Markov parameters are mapping the inputs of the system to the outputs of the system directly without thinking of the internal state. And so in this system, it looks like CB, CAB, C, A to the power n times B. So B, remember, is our input matrix, C is our output matrix, A is our state update matrix. And so if we look at the regression problem, we can see we're really kind of regressing Y against this product of the current input with the past inputs. I can write it as a Kronecker product of this form of U bar, which is like a history term, times UT. And so this is ultimately linear regression with the following data matrix that has rows which are dependent on each other, right? Each row, if I ignore this part, is almost exactly a copy of the row before, shifted by 1. That type of matrix is called a circulant matrix. But it's not exactly a circulant matrix because I also have the product with the different inputs. So some kind of highly dependent random matrix. Okay, I guess I'll tell you what we can say in this setting under the following assumptions. So we'll assume that the process and measurement noise, this is W and V, the noises affecting the system are IID 0 mean and have bounded second moments. The inputs are bounded. The dynamics are strictly stable. So the matrix A that controls how the state propagates has a spectral radius less than 1. The spectral radius is just the maximum magnitude eigenvalue. And so if this is less than 1, it means that the effect of this matrix decays over time. Geometrically, right? The history effect ends up being products of matrices or powers of this matrix. And so kind of what we can show, stated informally, on this Markov parameter estimation is that comparing the output of our regression with the true Markov parameters that I defined on the last slide, if I measure their error in the norm defined by the data matrix, so Z is our data covariate matrix from least squares, then I have the following guarantee on learning. This first term is kind of like a constant factor, roughly, depends on our failure probability delta. It's a 1 over delta dependence because I've made very mild assumptions on the noise. It depends on L, the length of the Markov parameters I'm trying to learn. And it depends on P, the input dimension. P squared L is the dimension of the Markov parameters in this case. So this is kind of the type of guarantee we might expect from like a heavy-tailed least squares analysis. And then there's constants that have to do with like the underlying system. How stable is it and how big is the noise? Like what are the second moments of V and W that I'm kind of hiding? Then I have a second term, and this term actually grows with T. So T is how much data we have. So it's growing with T, that's not necessarily good. I have some constant depending on the system. And then I also have this row of A to the L term. So because L is a parameter of my algorithm, I can set it in order to make that term small and not actually grow with T. And that kind of can give us, if I kind of grow logarithmically with T and logarithmically with the inverse of the spectral radius of A, this is kind of like a stability margin. Then with high probability, my estimation errors are kind of polynomial in dimension divided by the minimum singular value of this matrix. So I don't grow in T. I'm hiding log factors with this notation, but I'm not growing in T. If I want to actually argue state space recovery, so what am I estimating? I can actually make the same guarantee about the state space parameters, kind of using this Ho-Kalman algorithm and its guarantees in a black box way. So as long as there's some additional assumptions on those matrices, I can state the same form of guarantee about them. And then finally, to get to kind of a sample complexity result, if I use bounded random design inputs, I get kind of a square root poly dimension over T rate, which is probably not optimal in dimension, which is why I hit it with the poly dimension, but is the rate we expect with T, and indeed is the rate we saw in the linear case as well. Okay, so that was like a lot of the math justification to tell you that this algorithm kind of scales. I can provide errors both in a data dependent way and also a sample complexity analysis for a random design input, white noise. But to show you what it means, if I plot the estimation error over trajectory length for different values of L, I can sort of visualize the trade-off. For a very stable system, it's actually great to use a very small value of L. The reason being that I don't have to learn as many parameters in this case. And because the system is so stable, having a history of just, I think, 6 steps in the past, it's a biased estimate, but the bias is not large enough to degrade performance numerically. On the other hand, if I have a, very close to spectral radius 1, so something where it's not as stable of a system, the memory length is longer, then the short 6-length memory is not so great. It's much better to have a larger memory length, and the exact best one kind of just depends on this trade-off between the dimension and the decay of memory. Okay, and this plot kind of summarizes that, right? So for less stable systems, it becomes more important to have a long enough memory. Okay, so to kind of summarize this, learning dynamics from bilinear observations, our approach was kind of a least squares with a particular type of nonlinear feature. The analysis, which I'm not going to have time to discuss further, had to look at that random matrix I pointed out, that Z data covariate matrix, which had a kind of a complicated dependent structure. For that, we used kind of a blocking technique, which I don't think is new to everybody, but it was kind of new to this literature. And the exploration strategy is actually very similar to the linear setting. It's perfectly sufficient to have white noise exploration again. So, and the guarantee we get from that looks a lot like the linear setting, except for maybe some dimension questions. Okay, so that's the learning side of things. Yeah. Now, what I would like to do is kind of ask the same question that we asked and partially answered for linear control is, that's great if we want to learn parameters, but what about actually controlling the system? What do I need to know to make good recommendations, let's say? And so here's like our attempt at this problem so far. And this is where a lot of the open questions are. So, okay, the optimal control problem is in the same setting. Linear state updates, bilinear measurements. We considered a slightly more general form of bilinear measurements where we could have m-dimensional outputs instead of just one-dimensional outputs. So I'm kind of writing it in this way, but same idea. I have products of U times the matrix C. So to point out, if all of these CIs were 0, this would be a classic linear problem. If this C0 is 0, I can do some remapping to get to the learning result. I'm now going to put quadratic costs, so very similar to the linear quadratic problem. And our motivation here, I guess, I know I was talking about personalization before, but with this type of cost, I think it's more of a regulation or stability goal. So it might make sense to think about robotics, where we're trying to like keep a drone in the right spot. But where, I don't know, I guess our electrical engineer was pretty bad. And so every time we try to send force, we try to actuate by sending voltage to the motors, we like mess up our sensor a little bit. I guess that's kind of the model you could think about. And then we'll also assume for this optimal control case, Gaussian process noise, measurement noise at initial state. So now a stronger assumption on the noise characteristics. And then the last thing I want to define is the information set for decision making. So if we make a decision at time t, what information do we have available to do so? We have the past inputs and outputs, but actually a little bit of delay, only up to time t minus 1. And that's because our model says that the output at t depends on the input at t. So we can't actually, we can't see output yt until we've chosen ut. So this is off by 1 compared to the classic setting. But otherwise, if I kind of put this all together in an optimal control problem, this is really just a small departure from classic LQG control, linear quadratic Gaussian control with partial observations. And this is recent work that I've done with Yaya and Yasir, who also worked on the learning stuff with me, with my PhD student Sunmuk, and with Mariam Fazil at University of Washington. Okay, so the separation principle I mentioned before is the idea that for linear control, at least, it's sufficient to independently design estimation and control. It's a very convenient paradigm also, regardless of if it's optimal. And right, there's two components of the separation principle policy. There's state estimation, and then there's a state dependent policy. So we're going to consider the separation principle for this problem and try to understand, is it okay to do that? For state estimation, things are rosy, things look good. So we can use a Kalman filter very similar to in the linear quadratic Gaussian case. The Kalman filter is this kind of almost linear update where my estimated state follows the dynamics using my previous estimated state, my input, and then I have some correction term that corrects what I actually observed compared to what I expected to observe. Now, there's a difference because this C actually depends on the input, but it's sort of a small difference. I also have my gain. That's how much my estimate changes. And the gain is defined mainly in terms of the state covariance. So in addition to actually updating the estimate of the expected state, I'm actually tracking the state covariance. I don't have that much time, so I won't get into the details of Kalman filtering, but this is a classic Kalman filter that you would learn in, I don't know, I guess if you're an EE undergrad in an advanced class, maybe. So we show, and I guess this is trivial, but the posterior distribution of the state given the information available at time t is exactly a Gaussian distribution with mean x hat and covariance sigma t. Which is computed by the Kalman filter. So Kalman filter is doing exact, perfect, I guess, optimal estimation statistically. So that's good. And the only difference, I guess, compared with the linear setting is that we have a nonlinear dependence on the inputs because this observation matrix C is a function of the input in some sense. And so it's appearing in many more places than the input would normally appear. Normally, the input would only appear here. And this is kind of the crucial difference in this optimal control problem. So we do a quick example of, if you really squint, this is the dynamics of that quadcopter I talked about before, where I have a single input, which is force, some kind of force, which I guess it's a voltage, and single output and, single input voltage, single output, which roughly corresponds to looking at the position, but somehow my position sensor is corrupted by that same voltage as well. And so we can just say, does the separation principle work? So we compare in blue perfect state observation. So if we knew the state, this is kind of the cost we could achieve over time. I'll start with this plot. We compare it with the classic partially observed setting where C1 is 0. So I just have, then this is 1. So I'm just actually uncorrupted, observing the position in a noisy way. That's the black line here. So you can already see like partial observation does degrades performance. This is well known, but we do know it for this black line, this is the optimal performance. It's really the best we could expect. Now, if we switch and have a fully corrupted signal, so we kind of only observe the position when we're applying a non-zero force, the cost is much worse and actually cause quite high variation, in some instances increasing linearly with time. So why is this happening? If we look at the input over time, now remember the input is defined as a linear function of the estimated state. all of the inputs kind of go towards zero at the end of the horizon. This is actually mainly an artifact of the linear policy. It's optimal in this case from the control perspective only to apply less input at the end of the horizon. It's kind of saying like you don't really care that much because you're about to be done. For the LQG case, this doesn't really have any effect on the common filter, state estimation error, or the trace of the covariance matrix. But you can see in the bilinear case, our errors kind of increase, I guess, exponentially towards the end of the horizon. What happens is at the end of the horizon, we stop applying input. We stop actually observing the state. The common filter is statistically optimal. So the common filter is able to tell us through its covariance that like, yeah, this state estimate is blowing up. But because we're not considering filtering at the same time as control, we don't know this and the policy performs badly. Okay, so I think I'm pretty much at time. So I'll get to the punchline. For any horizon length greater than 2, the optimal policy is not affine the estimated state. And so the separation principal policy is not optimal. We show instances where the separation principal policy actually locally maximizes the cost. And in these instances, the optimal controller is actually nonlinear, and it's also not even unique. So this is very different from the like nice closed form solutions we could have in the fully linear case. I don't want to show you the full proof sketch, but I do want to show you this picture, which is to say in red, we have our classic LQG problem. And in black here, we have certain instances of the bilinear problem. And what you can see is the cost in the bilinear problem is kind of the sum of two components, a quadratic, which is kind of the control side of things, and basically a bump centered at a particular location, which is the estimation side of things. That bump says if you choose kind of the wrong input, you observe nothing, and that's bad. So it's locally maximized when you choose kind of zero input or effectively zero input. Depending on some of the parameters, this bump can be exactly aligned, making this a local maximum and two non-unique local mins, or it can, actually be fine. Separation principle was a great policy, or, the functions look different, but the minima are almost the same. And so it's actually kind of a complicated and interesting story. I'll summarize to say that's an open question. I would love to work a little more on the learning side. Definitely think about how to design controllers for this simple optimal control problem, and then put it all together into kind of a full sample complexity analysis. What do you have to observe about this system in order to properly control it? And yeah, I'll end there so that there's some time for questions.
Thank you. So let's thank the speaker. Are there any questions? Let's see. Can I maybe then start discussion? When you were telling that you tried to use on your drone, but there was some issue with measurement, I maybe didn't capture quite right. I thought that this adding uncertainty and noise was exactly to capture the errors in measurement, no?
Yes. Okay. So yeah. So
apologies, but
yeah, no, that's a good question. So this is just kind of get intuition, I guess, for what's going on here. If I have a drone, let's say, normally like I have some fixed sensors that tell me about the position of the drone, let's say, and they tell me about the position of the drone equally well, regardless of the state or regardless of the input that I choose. In the bilinear case, I'm complicating that in a kind of a simple way by saying the quality of my sensor actually depends on the input that I've chosen as well. So in the drone case, it would be something like the voltage that I'm sending to my motors, that's like the input for force, is somehow also messing with my sensors. That's maybe a way to think about like what this model is saying. And I say the quality because the ratio of this noise to like this coefficient is kind of like a signal to noise ratio. And so this coefficient changes in a input dependent way. So yeah, I guess in the linear case, you would not have modeled this. In the linear case, this term would be gone and it would miss this because this is also kind of modeled as independent.
So, but then you say this voltage is actually not in the CIs. It's
This U would be a voltage, let's say. That's kind of
okay. But yeah.
I mean, this is not like I'm not going to claim this is physically realistic, but that's kind of what it's getting at.
Okay. Okay.
Yeah.
Thank you. So that was,
Yeah.
there is one more.
So I don't know whether you were at my talk yesterday, but so we have gained a lot of, I think, mileage by taking the stability principle, by considering multiple modeling choices, but we haven't done anything in the time series domain. So I wonder whether this is relevant here, that you could have made, it's hard to believe that you could have made another reasonable modeling choice. And to see whether if you consider 2 or 3, whether they'll give you actual stability beyond just one particular model for design. Because as I showed yesterday, we did gain a lot by considering multiple choices into like biological case studies.
Yeah. So I guess in this case, we're kind of understanding what happens if you assume this structure on the time series, right? You have linear dynamics, bilinear observations. And so I guess the class of models is then like any A, B, and C matrices, right? That's kind of describing everything that's considered. And I guess I'll say as a subset, you actually recover the linear case. You could always learn that these are all 0. So in some sense, like this is expanding the linear modeling case. But you're right that there's, this is like, one step up from the simplest model you could imagine. And this is not, I guess this is more trying to make a comment on like fundamental trade-offs in learning and control, and less if you have real data, would I do this procedure? With real data, I think even this is like not rich enough.
I mean, at least you can easily put some constraints on the A's and B's, L1, L2, right? That's an easy variation on the linear. And you can have, just even right there, you can multiple choices.
Yeah, definitely.
For real data, I would be very curious to see whether that will help.
Yeah. I mean, so I think what is generalizable for the real data case, like the principle, I guess, that this could tell you in some sense, where is it? In the learning side of things, is really just like about this window. Like if you're trying to predict something in a time series, do you have to use the entire history of the time series, or is it sufficient to look at some finite window and like in a more autoaggressive way? Which is right, like if you have a finite context length, that's what those are all doing. This algorithm works when you have kind of a stability in the underlying process, which corresponds to some kind of loss of memory over time. And so I didn't have time to go into my future work or say more about that, but I think that's actually a flaw of this method, which is that it only works when by L time steps in the past, you've essentially forgotten what happened, or it's like an epsilon effect. It's more realistic to consider like some persistence of memory.
But for control, I don't think you necessarily have to have parameter estimation or predictions are enough for you to do something. And then if you do prediction, then you can do the exponential tapering off without explicitly having a window.
Yeah, well, so in some sense, this like Markov parameter, I'm analyzing the estimation errors of the parameter, but this is actually, you could analyze the prediction errors of this parameter as well. The reason that parameter error is useful to look at is because in control, once you design a new policy, you shift the distribution of your data from what you may have seen during collection. And so having a guarantee on prediction on data that you saw doesn't really help you in guaranteeing how the policy will perform when you deploy it. And that's actually why the parametric perspective, that's what it gives you.
There's one thing about the theory, the other is more empirical. You can also make a case that the multiple models also give you more power to transfer to, because it might have different structures.
Right.
Thank you.
I think we will have to step our discussion here. So we have now lunch break, and let me remind you once again that we have a today photo shoot. So like we will be here, meet at the 1:45 outside, which means do not order pasta or anything with tomatoes that could kind of leave the stains. You need to look your best on the picture, okay?
My quote unquote add color to the picture.
That's true. Okay, thank you.